Evet, kaydı da başlatıyorum. Evet, 21 kişi oldu. Herkes iyi değil mi arkadaşlar? Koronaya yakalanan oldu mu aranızda? Umuyorum olmamıştır. Var mı lineer cebir öğrencileri arasında hasta olan? Evet. Sormak istediğiniz bir şey var mı başlamadan önce dersimize? Fatih Sait Duran. Gittin mi doktora? Yani var mıydı zaten yoksa yeni mi başladı öksürüğün? Bir aydır var diyorsun. Yani alerjik de olabilir öksürük. Ama gene de hani bir baktırsan iyi olur bence. Evet arkadaşlar. The reduce white point. Okay. Okay, so let's start. Let's start a new chapter. So this chapter is about vector spaces. So this will be a new concept for you. It's an abstract topic. So at first it will seem kind of difficult, but I hope you will get the idea eventually. Okay. So we start with section 4.1. So this section is a reminder of vectors in the plane and in tree space. Okay, so let's recall vectors in the plane. So by plane we write this r square. Okay, so this shows vectors in the plane. Vectors in the plane. So vectors in the plane. So what do we mean by vectors in the plane? We mean, so two numbers, right? There are two numbers, A and B. So this means a vector in the plane. And also vectors in tree space is R3. Vectors in tree space. So we show them by A, B, and C, like this. Okay. So these are three vectors, and these are two vectors, and these are three vectors. So they satisfy certain properties. So vectors in the plane and vectors in tree space, they both satisfy certain properties. So what are those properties? First of all, if we take two vectors, so and we add them, the order of the vectors really does not matter, right? So you can first add u and then v, or you can add v to u. The order will not matter. So geometrically we can show it like this, right? So if this is the vector u and this is the vector v, so if this is v and this is u, so you obtain the same thing if you go like this and then this. Okay, So the order does not matter. A second property is the parentheses does not matter. Uh, the parentheses does not matter, second property. So you can first add two of these vectors, right? And you get a result, and then you add u. It doesn't matter if you first add these two and then get this, add this two to them, okay? So it will give the same thing. So instead of this, you can just simply write u plus v plus w, okay? Third property is there's a certain vector which is called the zero vector. And if you add this vector to any vector, you get the vector again, okay? So this is like number zero. So it is like an identity element with respect to addition. So what is this zero vector? So this zero vector in R2 is really 0, 0, okay? And in R3, what is it? It is this 0, 0, 0. Okay. So this is called the zero vector. So this is called the zero vector. Okay, another property is each vector has like an additive inverse. So if you get a u and you add minus u, you get 0, right? So what does it mean? So if you add, so if this is the vector u and you add minus u to it, you get the zero vector, okay? So this is the fourth property. So these are all the properties that I think you know. So they are kind of boring. But in the next slide, we will see that this is a very like a general idea. So we will generalize this, okay? Okay, so the next thing is, so now the relation of this vector addition with scalar multiplication. So if you first add these two vectors and then multiply it with a scalar, okay, it's the same as doing this operation. So it's distributive property, dağılma özelliği, right? This is called distributive property. So same thing holds here. Okay, so these are all elementary properties. And another property is, again, the parentheses does not matter for scalar multiplication. And the final property is if you multiply a vector by the scalar 1, then you get the vector itself. So these are like 8 properties that are known to hold for vectors in R2 or in R3. Any questions here? One thing you can ask is what we will do with this thing. So we will see that this idea really generalizes to solutions of linear systems, okay? Solutions of linear systems have a similar structure. And knowing this general structure will help us understand more about the solution space of linear systems. That's all I can say for now. We will see it, okay? Sorusu olan var mı arkadaşlar? Sorabilir. Okay. These are this is all about vectors in the plane and vectors in tree space. So this is all about section 4.1. Now let's go to section 4.2. So here there's a abstract concept of vector spaces. Okay. So this is we will be talking about real vector spaces. Okay, and there's also a version of complex vector spaces, but we will not talk about it. Very complex. So there's also complex vector spaces. So in this course, we will only deal with real vector spaces. Okay. And there are other versions of vector spaces, real vector spaces, complex space vector spaces, and there are others. So probably you will never see them in your life. Maybe you will learn something about complex vector spaces, but that's it. So there are other vector spaces as well. So what is a vector space? So vector space is really a set. Okay, it's a set with this label V. Okay, so it's a set of elements, and it has two operations on this. There are two operations on this set. One is shown by this interesting plus formula, O plus, let's say O plus, and there's an interesting multiplication operation, which is O dot. Okay, so a vector space is a set. You know what a set means. Set means a collection of elements with two elements, with two operations, O plus and O dot. And it has to satisfy certain properties which are grouped here. Okay, so vector space is a set with two operations, and those operations satisfy these oh, I'm sorry, so satisfy these properties. Okay, so these kind of 8 properties here listed here. And if you look at these properties, they are really the same properties we have seen in the previous slide. Okay, so all these properties, if a vector, if a set with two operations satisfy these properties, then we call that set with those operations a vector space. So let's go over it again. So first of all, this O plus operation. So if you take any elements of this set V, then UO plus V must be in the set. So sum of two elements of V must be in V. Okay, that's the first condition. This is known as being closed under the operation O plus. So if you O plus two elements, then the result is still in the same set. Okay, so it's all kind of abstract. We will do a lot of examples, don't worry. So, and this addition operation, O plus operation, must satisfy this property, which means the order does not matter. The second property is the parentheses does not matter. Okay, these are all imitations of the vectors we know from the plane and tree space. Okay. Third property is there's this zero vector. Okay, there's this zero vector, and if you add any vector to it from left or right, you get the vector itself. Okay, so this zero vector is really like an identity element for addition, vector addition. Third property is each vector has an inverse with respect to vector addition. So if you add a vector to its additive inverse, you get the zero vector. Okay, so again, let me show you. So we're it's going in this like all these properties, right? The same properties. Nothing changed. So this one, this one, this one, this one. We have gone over these ones. What is the next one? What is the next one? So we also have a second operation, as I said. So this is called O dot. And this O dot operation satisfies these properties, these like boring looking properties. Okay, what are they? So if C is any scalar, okay, scalars here are real numbers. That's what it means to be a real vector space. Okay, this real means that the scalars are reals. For a complex vector space, the scalars are complex numbers, which I think you may know, or doesn't matter for this course, but complex numbers are also numbers. And there are other numbers as well, other than real numbers and complex numbers. And they are sometimes useful, like quaternions, things like that. They are useful in physics. Okay? But we won't be doing those things. Don't worry. Okay, so okay, again, this is what is this? This is a distributive property. So distributive property of scalar product, or O dot, with respect to O plus, or vector addition. And sixth property is a similar distributive property. And the seventh property is, again, like an associative law for scalar product, which is the parentheses does not matter for scalar product. And the eighth property is, if I take the product of any vector with the scalar number 1, then the result is still the same vector. Okay. Okay, so we said that this V is a set, and we will call its elements, if it satisfies these properties, these 8 properties, we will call its elements as vectors. Okay. And the elements of the set of real numbers are called scalars. There is this distinction between vectors and scalars. This O plus operation, we will call it vector addition. And O dot operation, we will call it scalar multiplication. These all resemble our known operations, okay, from the vectors. This 0 is called the 0 vector, and this minus u is called the negative of u, just as in for normal vectors. Any questions? Let me know. Now we will see examples, okay? We will talk about a lot of examples. Okay, if there are no examples, let's go over them. Our first example is Rn, which is the set of n vectors, okay? So we already talked about R2. Okay, so these vectors A and B. So we check that they satisfy all those properties. So R2 is a vector space. R3 is a vector space. Okay, A, B, C, not equal, but R3 is the set of all vectors of this form, A, B, C. And in general, if we have, for example, R4 is also a vector space. So it has, so let's write x1, x2, x3, right? x1, x2, x3. So it has 4 components. So this is a vector space. So if you add like 2 vectors of this form, it will still be a vector of this form, and all those operations and properties will be satisfied. So there is nothing interesting in R4. It's the same thing. And this is true for any n, right? Any n. So it is true for R5, R6, R7 is a vector space, R8 is a vector space with usual vector addition and scalar product. Okay, there is nothing interesting here. So let's move to the next example. Next example. Okay, so what about matrices? Well, matrices are also vector spaces, the set of all matrices. Okay, so this thing all is important here, the set of all matrices, all 2 by 2 matrices. Okay, so let's show this by M2 2. So M22 is the set of all matrices of this form: A1 1, A1 2, A2 1, A2 2. So we're talking about the set of all such matrices. Okay, we're not talking about the specific matrices matrix. We're talking about all such matrices, and they form a cluster or like an object which is called a vector space. Okay, so when we say it's a vector space, we always have to like tell what the vector addition and scalar multiplication is. For this vector space, vector addition is the usual matrix addition. Okay, we know how to add matrices. So it is the vector addition for this vector space. And we know the scalar multiplication for the matrices. So the scalar product for this space is that usual scalar product. Okay, any questions? Shall we go and check those properties? Maybe yes, right? So let's go back. Let's look at this slide. So now, okay, for M, we are talking about M22, 2 by 2 matrices, the set of all 2 by 2 matrices. So now if I take a vector in M22, a vector is really a matrix. Okay, now because elements of M22 are matrices. So the vectors in M22 are really elements of M22, and elements of M22 are matrices, 2 by 2 matrices. So if we look at it, so we defined the vector addition, which is really the matrix addition, and the scalar multiplication is multiplying the matrices by scalars. Now, what about these properties? So yeah, we know that for matrix addition, the order does not matter, the parentheses does not matter. There is a zero vector. Now, what is the zero vector for M22? What is the zero vector? Oops. What is the zero vector here? Any ideas? All zeros, right? So it's this one. 0, 0, 0, 0. So if I add any matrix to this one, I will get that matrix again. Okay? Bir de şey oluyormuş arkadaşlar. Mersem ben tek başıma anlatıyormuşum burada. Herkes kopmuş. Hoş olurdu. Okay, so zero vector for this vector space is the 2 by 2 matrix of all zeros. Okay, so let's go back. So we're in this property. So we have really a zero vector for this vector space, and the additive inverse or negative of any matrix is you multiply each element by -1, and you get it. Okay, and these properties are all trivial. You can check it very easily. Okay, so if you add two matrices and multiply it with a number, it's the same as multiplying that matrix with this number and the other matrix with that number and adding them. They are the same thing. Okay, we can check it. Let's just look at that property. Okay, so let's look at this property just for checking. So this is property number 5. Now I will show you that this property really holds. So I get two vectors. Now, as I said, vectors are now matrices. So if I do this operation, what do I get? I get C, A plus E, B plus F, C plus G, and D plus H. Okay? And if I multiply by C, what do I get? I get C times A plus E, C times B plus F, C times, oh, this is the same C. Doesn't matter, right? Let me change this to K then. Okay, so let's make this K. I don't want to use same thing. So this is K times C plus G and K plus D plus K times D plus H. Okay, so this is one side. Let's check the other side. What does the other side say? So it's this one. E, F, G, H. So you can really see that this is the same thing. So it's too much writing here. KB, KC, KD. And what about the other matrix? Let's write it. KE, KF, KG, and KH. Now, if you add these two things, you can see that this one equals this one. Okay? They are the same thing, right? Because they are the same thing. What can I say? So here we only checked property number 5, but all those properties can be checked. Okay? So you see, it takes too much time, so I don't want to do all of them. But I want to talk about different examples that we will come up with. Okay, so we just verified the property number 5. Let's go to the next. Do you have any questions here? Let me stop for a minute. Do you have any questions? No. Okay, let's continue. So how can we generalize this example? Well, we can talk about not 2 by 2 matrices, but m by n matrices. So for example, m 2 by 5. So all matrices which have 2 rows and 5 columns, they're also vector spaces. There's nothing special about 2 by 2 matrices, okay? This is also a vector space. All those properties can be checked. And in general, the set of all m by n matrices with usual matrix addition and scalar product is a real vector space. So all the things we said about 2 by 2 matrices are true for m by n matrices. So m by n matrices, the set of all m by n matrices, is a real vector space with those operations. Okay. Okay, so yeah. So this is a little bit more interesting example. The set of all 2 by 2 matrices with trace equal to 0 is a real vector space. Maybe I will talk about this example in the next section, okay? So let's skip this for now. Let's skip this for now. I will talk about it in the next section, okay? Okay, let's continue. Well, this is an interesting example. The set of all polynomials with degree less than or equal to 2. With polynomial addition and multiplication by scalar is a real vector space. That is kind of interesting. Let's look. What are the elements of P2 now? So P2 is the set of all polynomials, right? So I can write it as A times bx plus cx squared. Okay, here A, B, and C are just real numbers. So the set of all polynomials. So this is really the set of all polynomials of degree less than or equal to 2. Now, how do we add two polynomials? Well, if I want to add two polynomials, for example, a plus bx plus cx squared. So this is one polynomial. Now I'm defining a polynomial addition. Well, let's write d plus ex plus fx squared. So if I write this, we know this is how to add them, right? So this is the usual addition of two polynomials that we have seen in high school. So this is a plus b, no, a plus d, I'm sorry, a plus d plus b plus ex plus c plus fx squared. This is the usual polynomial addition. Now, what is the scalar product here? What is c? Oh, I couldn't do it. C O dot. Let's write a plus bx plus dx squared. So how can we define this? Well, we can define this in the usual way. So this is really ac plus bcx plus dcx squared. Okay, so this is P2 is really the set of all polynomials with degree less than or equal to 2 with these two operations. Now, let's go back to our definition slide. Okay, so this is the definition. Now, you see for adding two polynomials, the order will not matter. That's for sure. We can, the parentheses will not matter because it doesn't matter for numbers. Okay. What is the zero polynomial? Well, the zero polynomial, what is it? It's really the polynomial which takes which sends any x to 0, right? So it's the zero polynomial. So zero vector is now the zero polynomial. Okay, so zero polynomial, what is zero polynomial? Zero polynomial, where is it? Now let's define the zero vector. Zero vector is really this polynomial ox which sends x to 0. So this is the letter, okay? So it sends x to 0. So this is a polynomial, and this is really the zero polynomial. So if you add it to any polynomial, you get the original polynomial, right? And each polynomial also has an additive inverse. So let's check. Let's go back to this slide again. So we talked about scalar product of polynomials. So you can see that all these properties are really trivial. So if you multiply any polynomial by 1, you get the polynomial itself. Okay, so I hope I convinced you that P2, the set of all polynomials with degree less than or equal to 2 with these operations, is a real vector space. Now we can generalize this to Pn. So this is not just true for 2, but this can be generalized to any n. Okay, so the set of all polynomials with degree less than or equal to n is a vector space. Any questions? No? Okay, we are still generalizing things. Okay, so not just polynomials with like degree less than or equal to n, but in general, the set of all polynomials with polynomial addition and multiplication is a real vector space. Okay, so you can add. So yeah, what can I say about it? So if you add any two polynomials, the result is a polynomial. The idea is that, and if you multiply any polynomial by a number, the result is still in the same set P. And we can still generalize this. Okay, we can still generalize this. This is not true for only polynomials, but this is true for the set of all functions from real numbers to real numbers. So polynomials are a special class of functions, and we can generalize this example to a general set of all functions. Okay, the set of all functions form a real vector space. Okay, now in this space, I see every function as a vector now. For example, f of x equals sine x, so this is a vector for me. Okay, and gx equals e to the x, so this is a vector for me. Now, how do I add two functions, f plus g? Well, I add them like adding two numbers, right? So this is sine x plus e to the x. And how do I multiply a function by a number? Well, I just multiply by, so this is again usual product. There is nothing fancy going on here. So the set of all functions, so what we have seen now is the set of all functions has a structure in it. Okay, it has a structure. It has a vector space structure. So you may start to think that, wow, everything is a vector space, right? So in theory, yes, everything is a vector space. So in all our lives, we were really living in vector spaces. So physics really deals with, so if you work in cosmology or if you work in quantum theory, you're always working in some vector space structure. There's always some vector space structure there. Okay. So yeah, let me know if you have questions. No? Okay, so far we have seen examples of vector spaces. Now it's good to identify when a given structure is not a vector space, okay? So we always talked about vector spaces. Now let's talk about non-vector spaces, okay? Our first example is this. Let V be the set of all real numbers. Okay, so our set is really the real numbers. This time, I'm defining the operation u plus v as u minus v. Okay, so very strange. Okay, so what does this mean? So if I really write 2 plus, I mean 3 o plus 2, this really means in real numbers 3 minus 2, and the result is 1. So I can define this O plus any way I want. So you know, as computer scientists, you can define any function you like, right? So you define O plus takes 2 arguments x and y and sends it to x minus y. Can't I do this? I can do this in the computer, right? So I can do this in math too. And how about scalar multiplication? Well, scalar multiplication is the ordinary multiplication. There is nothing fancy here. Now, is this a vector space? And if it is not, which of the properties are not satisfied? Let's go back to our definition slide. So it's kind of getting messy here. Let's look at the first operation. So let's look at this one. Does it satisfy this? Is this property satisfied? Jewish world, what do you mean b equals 0? Kramer is right. In previous example, let's go. I don't understand what you said. What is v equals 0? I don't understand what you mean. Anyway, if you can ask me by turning on your microphone if you want. In the previous example, I take the plus function as it is a regular math. You mean this example? This one? 3 plus 2 is really, according to this definition, 3 minus 2 equals 1. So 3 plus 2 in this structure, it is defined as 1. So we define 3 plus 2 as 1. Maybe. Okay, let's go back to our definition slide. Does it satisfy the first property? So is 3 plus 2 and 2 plus 3 same thing? No. Okay. So because 3 plus 2 is 1 and 2 plus 3 is minus 1 now, according to this definition. So the first property is not satisfied. So this one is not satisfied. Let me use this one. So this one is not satisfied. What about the second one? Is the second one satisfied? So you can give numbers to them. So like 1, 2, 3. If you give 1, 2, 3, what is 1 plus 2 plus 3? So this is not usual plus, but all plus. So what is 1 plus 2 plus 3? So 2 plus 3 is minus 1, right? According to this new addition. And 1 plus minus 1 is what? So it is 1 minus 1. 1 minus minus 1, it is 2. What about 1 or plus 2 or plus 3? So now you do this part first. What is this? What is this? This is minus 1. O plus 3. So what is this thing? Oops. Not no. What is this thing? This is minus 4, right? Did I do it wrong? I agree with Muhammed Eren Ünlü. I don't agree with Sena Altıntaş. I think it's minus 4. So yeah, so this property is not satisfied. You can write it for general ABC as well. So if you take A, O plus B plus C. So what is this? This is really A minus B plus C is B minus C. So this is A minus B plus C. And what about A plus B plus C? So this is A minus B minus C, which is A minus B minus C. So you see, these two are not equal. Okay. So the second property is not satisfied as well. So do we have a zero element? Is there a zero element here for this operation. So remember, the zero element must satisfy these two properties, these two conditions. So u plus 0 is u, and 0 plus u is u. Is there such a zero? Nesrin says yes. Ahmet Emre Sarcan says yes. It's kind of tricky. Let's look at it. Let's look at it. So if there is such an element, let's not say it's zero, but let's write z. So z plus any number u is u, and u plus z is also u. So this is true for all u. For all u. So what does this mean? Z minus u is u, and u minus z is u. And this is true for every u. Is there such a z? Minus 1? No, minus 1 will not do it, right? So if I minus 1, if I add minus 1 to 3, does it give me 3? Is this equal to 3? No, right? Because this is minus 1 minus 3. So minus 1 minus 3 is not equal to 3. So there is no such element. That's what I'm trying to say. Z minus u equals u. Yeah, so we want this to hold for one z and every u. Okay, remember, our new fancy O plus is really subtraction. So z O plus u means z minus u. Z minus u equals u. We want this to hold for every u and only one z. Okay, remember, not z is fixed. Zero vector is fixed. For example, let's try to find the inverse of I don't know. Let's try to find the inverse of 3. So what is the inverse of 3? So this means z minus 3 is 3. So we guess we found z, but we also want this other property to hold. What is it? We want 3o plus z equals 3. So we want this to hold 2. Now we are choosing z to be 6. So this means 3 minus 6 equals 3. Wow, it doesn't work, right? Okay, what I'm trying to say is there is no zero element for this subtraction operation. Okay? There is no zero. So if there is no zero, then there is no way of talking about minus element because it depends on the existence of zero element, zero vector. So none of these properties 1, 2, 3, 4 are satisfied. But if you look at the other properties, well, it's satisfied for the other properties. Like the 5 is satisfied because u o plus v means u minus v, and we know that multiplication is distributive over subtraction. So property number 5 is satisfied. Property number 6 is satisfied. 7 is satisfied, and 8 is satisfied. Those are all satisfied, but the first 4 conditions are not satisfied. So let's go back to the question here. What? What is this? No, this is not, okay. What is this? 2, 3, 4, 6. What is, there's also, I should write, what? I'm sorry. So that should be 1 here. Let's check property number 6. I think I made a mistake here. Let's go back and see if number 6 is satisfied. So this should be satisfied, right? So this should be satisfied. What is, so this is the usual product. Oh, it's not satisfied. I'm sorry. So C plus D u. What is this thing? So this is really c plus d times u, the usual u times. Okay. What about this side? What is c dot u? So this is cu o plus du, and this is cu minus du. So I was a little bit going fast here, so property number 6 is not satisfied. I'm very sorry about it. And what about property number 1? Property number 1 is not satisfied, right? So we should really say 1, 2, 3, 4, and 6 are not satisfied. So even if one of them is not satisfied, it means it's not a vector space. Okay, so if all the conditions are not satisfied, then it is not a vector space. Okay, now let's fix this thing and give a break. So there should be 1, 1, 2, 3, 4, 6. Okay, thus V is not a vector space. Let's pause for 10 minutes. So it's 1:52. Let's meet at 2:52. Okay, 10 minutes break. So I'm stopping this.